So y'all, before I move away from the uh, lead screen, I want to make sure I talk about the image that's on the screen. So that's actually a picture of the Frank-Hertz experiment at work. So that is the chamber looking into the neon experiment. And if you can see it, those are three different lines or bands of of neon atoms that have been excited. So as we spoke about yesterday, if you look at the part one of this video, the electrons push into the neon gas. It excites the neon molecules if it has enough energy. At a certain point, when the energy gets high enough, the elastic collisions turn to inelastic collisions. That's when it actually deposits energy into the atom. So on the downward slope, the atoms are starting to get excited. Then when the atoms are the electrons in the atoms drop down to their ground state again, they release photon, and that's the first band at the top. But then what happens is, as you look at the experiment and the voltage increases, those electrons that lost their energy at the first band of neon molecules are accelerated again, and eventually they go fast enough to deposit energy into the second band in the middle and start having inelastic collisions again, lose energy. The atoms that gain that energy lose that energy again and emit a second band of photons. And then the voltage is high enough now that those electrons are accelerated again. Then they hit a third band of molecules, and you can see the row at the bottom of neon light. And then those electrons start to uh, either go into the uh, anode and get recorded as voltage or fall off. But that's how we get the three different bands. So that's pretty interesting. And I'm glad I took a picture of it that day because we couldn't see it the second day. The professor says sometimes it's very light, but that day, and of course it was the first day we did the experiment. So maybe some of the gas moved around, is not as focused there. I'm not sure. But that day we was able to get a good view of it. And took several pictures of it, and that was the best picture right there, where you can see all three lines. You can see the sort of column of pinkish color, but you can see a little dim area in between, and that breaks it up into three different bands. So voila, the quantum aspect of matter at work. So I'll go ahead now and we'll start going through this paper. We'll continue through this paper here. Remember to subscribe to the channel if you haven't. Make sure you like this video, share it, and I also have my page shown, my X link. I'm on Discord right now. So if anyone joins and want to come on Discord to talk afterwards, so may have a little bit of time to talk. Actually have a new linear algebra assignment that came out today. So I'll go ahead and do that assignment soon. But for the time being, I do have a little bit of time. I'll see how long it takes to get through this paper. As a reminder, we started with the introduction and the part two of the textbook. We saw how the electrons lose energy as they hit the atom and have an inelastic collision. We saw how there's a cycle of elastic to inelastic collisions. Let's see what that particular part is. Right here. So originally they thought it was something else, but now we know that the peaks occur at spacing of about 4.9 electron volts. The reverse dip corresponds to electrons that lose all their kinetic energy. So right here, basically the electrons are gaining electric energy, at least elastic collisions on the uprise. At the peak, the voltage is enough where they start depositing their energy, you can say, into the atom. Thus, after the electrons hit, they lose energy, so less makes it to the anode, so it's not registered as current. But then the electrons start to gain more energy enough to have elastic collisions. They bounce off and register as current. Then they no longer register as current. So that's pretty interesting, and I understand that a bit better after a good night's sleep. So what I'll do is continue on part three. Electron exchange is a significant excitation mechanism. I may get silent along the way as I take notes, and because I'll have to put this on a paper, and then I have an oral exam to speak on this as well. So what I'll do, let me move my camera to the side just a tad bit. I'm not really sure what's up with OBS, where sometimes things, I guess I'll just move things unintentionally somehow. I'm still not sure how, but I don't know, just try to adjust the size of this entire thing instead of everything individually. And eventually I'll be pretty good at this. At least my sound is better. Looks like my volume is okay. I'm not having to scream to be heard. So I'm getting better at it, but I still have a lot of work to do to understand this well. All right, so electron exchange is a significant excitation mechanism. The first excited state in Mercury, the first excited states in Mercury are known to have mainly triplet character. So he's talking about figure two. So it looks like the first excited state is in this section here, i.e., or to clarify, the dominating configuration consists of two valence electrons in the 6s6p orbitals, giving a total p state where the spins are coupled to a total spin with quantum number s equals 1. Obviously, I need to brush up on my uh, placement of electrons and atoms to understand this clearly. The spin-orbit interaction splits this configuration into three states, 6-3p0, 1, and 2, with total angular momentum quantum numbers j equals 0, 1, 2. Now, I know I'll be talking about that again. I took quantum once as a pass-fail class. I'll take it again as a grade this fall, and we definitely had to do some angular momentum calculations. So this is a good prelude, which is what interested me about this experiment. The states with j equals 0, 2 are metastable, which means they cannot decay into 6-1s ground state because dipole emission is forbidden for transitions with change in s equals 0. And in particular, j equals 0, 2 to j equals 0. The strong spin-orbit interaction within the mercury atom results in a small but significant singlet admixture to the 6-3p1 state, i.e. this state is not a pure triplet state, along the well-known optical transition 6-3p1 to 6-1so, 254 nanometers in intercombination line. Now, I remember a professor saying that the emission for Mercury is at 254, which is why we can't see it visually, which is why there is no port. So Mercury emission is at 254 nanometer. And let me actually go back to my notes. So we need to write a paper lab manual. So here's my lab manual for my class here. I have blur on, so it's not picking it up too well. And I'll see exactly uh, where I noted that at, because I know he said it. And I'll make sure to connect those two things. Right? We turn on the light. So we have here. So my notes from professor. energy electrons excites Mercury, falls, excites another, falls, excites another, a long path of travel. The greater voltage accelerates the same electron again farther along while the line moves down. 250 nanometers of light release. And this is for Mercury. So this is corresponding well. Did I scroll this page? I guess I scrolled it by mistake. So I guess you could say 250 to 254. So that would be about 2500 to 2540 angstroms. And I want to see where they mentioned the angstroms. Yeah, they mentioned it here. All right. So that's 2536. Why don't we stick with 2536 angstroms? And that is for mercury emission. And why don't I take a look? Uh, there's a lot of sort of charts that show what wavelength goes to what part of the EM spectrum. So let's check this out. So looking up online, 254 nanometers. Yep, so that's in the infrared. Oh, no, no, I'm in infrared. Hold up. Saying 1000 is in the infrared, or close to the infrared. I don't like this chart. See if I can find a good one. There we go. I think that chart had a different units. So let me share this. So I'll switch my share to so this is the image here. So we have, this is in meters, so it's easier to read. So we have 254 nanometers. That's 250 times 10 to the negative 9 meters. And here is 10 to the negative 9 right here. So we can see it's in the ultraviolet range, which is why we can't see it. So when it's mercury, all right? And this site is the NIST.gov site, so I'll make a note of that. I actually like this image a lot. And I'll go back to the article. There we go. Everything seems to be working properly. So let me make a note of this link here. So I will be, I mentioned yesterday, I'll say it again, writing a paper on this for class, and I'll end up making a presentation. So I think I'll do for each of my experiments this semester, make a presentation on it, which I'll present. Maybe I'll see if me and MC Tune did my dark matter, dark energy talk on his channel. So maybe he'd be interested in having me on again to discuss the speed of light or Frank-Hertz, or maybe a few of them. Suppose not all of them could be an entire article, so perhaps I can maybe make a composite one with my favorite two or three. So we'll see how it goes. And this is the chart of the electromagnetic spectrum. All right, so back to the article. So now we're on the same page as far as the frequency that the light is emitting. I'm still unclear about the whole atom, the whole entire atom conversation right there left me. But I do understand that the transitions at this level of the mercury atom is emitting in a 254 nanometer interaction, which is the UV range for NIST.gov EM spectrum image. It is expected that 61S and 3P electron impact excitation is dominated by electron exchange collisions, leading to reactions such as, okay, so the electron hits the mercury. Okay, so right here it's saying the electron hits the mercury, the electron loses energy, and then the atom gains energy. So it looks like one of its electrons has an upspin, and then the electron goes to a downspin, which is interesting. Where the arrow denotes the electron spin orientations with respect to a given axis. That process is like one. That processes like one dominate the excitation of Mercury double upstates at low energies has been demonstrated more than 10 years ago in a special version of the Frank-Hertz experiment. So it's saying that the interaction here, the excitation of Mercury cause the Hg double upstate to dominate at low energy. And that's via the Frank-Hertz electron bombardment. I'm abbreviating Frank-Hertz FH. According to reaction 1, the spin orientation of the scattered electron will be changed in such a collision. Initially polarized electrons with polarization 5p were used, and the polarization p prime of scattered electrons was measured. Any value p prime over p less than 1 is direct evidence of exchange, provided that other interactions that could change the spin orientation do not exist. So if polarized electrons P were used. They're sent into the Frank-Hertz experiment. And then the ones that are scattered were hit or had an impact with an atom. So they called them P prime. And then they measured the corresponding spin of the P prime atoms. So why would P prime over P less than 1 relate to an exchange? Unless they mean that, it stands to reason that not all the atoms will scatter. At least not all the electrons will scatter. So we'll have to look at that. A schematic diagram of the apparatus used is shown in Figure 3A. Transversely polarized electrons results from elastic scattering by a mercury vapor beam passed through a filter lens that removes inelastically scattered electrons. The electrons are then deaccelerated and focused into a second mercury vapor beam. From the electrons scattered in the forward direction, those which have excited a certain atomic state and lost the excitation energy are selected by a cylindrical mirror analyzer. The transverse spin polarization P prime of the inelastically scattered electrons is measured in a Mott detector. I have the acceleration to 120 kiloelectron volts. So I'm going to look up a Mott detector. And what I'll do is I'll put this on screen. Mott detector. So, well, there's one in Nature, but that is an actual paper. There's in the description. Something other than a wiki site. What about some images of some Mott detectors? That should do. So now we're looking at some Mott detectors, seeing what they're about briefly. So, okay. So it looks like they're literally spin detectors, electron spin detectors. So a Mott detector is able to detect the spin of an electron. And let me expand the window a bit. There's actually a picture on the right side that's not showing in the uh, yeah. So that apparently is what a Mott detector looks like. It detects the spin of an electron spin detector. And let's take a look at this image. Quite interesting. And you notice the energy is in electron volts, which is customary. I'm starting to see. Okay, so my detectors detect the spin of an electron. And all right, so I was at the bottom line here. The initial polarization P is measured by tuning the electron spectrometer to zero energy loss. And we have figure 3A that was talking about the schematic diagram of the apparatus for direct observation of exchange collisions. Measured ratio P over P versus energy for electron impact excitation of mercury with a mean energy loss of 4.9 electron volts. And again, they seem to be using the Mott detector to do that. And I imagine that the lines here are the error bars, the error in accurate recognition of the spin. Figure 3b shows that measured ratio P prime over P for excitation for the 6,3p states at a mean energy loss of 4.9 electron volts. Right? So saying right here is about the 4.9. This is the energy loss that occurs most frequently in the Frank-Hertz experiment. Clearly, P prime over P less than 1, close above the excitation threshold, indicates that electron exchange is a significant collision mechanism. Electron exchange. As the probability for exchange decreases for electron energies above 9 electron volts, P prime over P increases and approaches a value above 1, a value of 1 above 9 electron volts. Above 9 electron volts, simple inelastic collisions without a change of spin orientation dominate by the singlet-like mixture of the 6,3p1 state. With this experiment, the importance of electron exchange has been demonstrated only for forward scattering angles. When the scattering angle is large, the spin-orbit interaction due to the motion of the scattered electrons in the field of the atomic nucleus may be significant. This prevents a straightforward interpretation of observed spin flips as being due only to exchange collisions. Recent experimental and theoretical studies of spin effects in inelastic electron-mercury collisions, however, have shown that, and I like that terminology, electron-mercury collisions, right there. So I'll make sure to use that terminology in my paper. However, have shown that exchange collisions are very probable, also at large scattering angles. It is beyond the scope of the present article to discuss these studies and an interpretation of their results. The interested readers refer to the original publication cited above. These investigations, however, show also another feature that significantly influences the probability for the energy losses observed in the Frank-Hertz curve. This will be discussed in section 4, which is called formation of temporarily negative ion states, resonances. So I remember Frank-Hertz originally thought it was an ion thing right here. So we'll see how it's related. This section is called the formation of temporary negative ion states. And let me see if anybody happened to hop onto Zoom, Discord. Not yet. I can see at least. Move the regular window where I can monitor it more easily. Right. So I have that here now. Right. So I'll be on the lookout if anyone does join. There are several experimental procedures that yield cross sections for the excitation of the resolved 63P012 fine structure states. The simplest method seems to collect the inelastically scattered electrons, but since the scattered electrons lose nearly all their kinetic energy very close to the excitation threshold, these slow electrons are difficult to detect. So when the electrons have an energy near enough to excite the mercury atom, they lose almost all their energy. And basically, I guess just sit there, don't much travel, hard to collect, whereas the ones that rebound elastically bounce off with the same velocity and they're very easy to bounce into a detector. In addition, such a measurement will require an integration over all scattering angles because apparently when they bounce off, they don't bounce in a particular angle. I guess some of them might bounce in reverse, some might scatter in the same direction, some might scatter at a near right angle. Very good results have been obtained in experiments where the excited metastable 6,3-PO2 mercury atoms were detected with channeltrons. Okay, see what a channeltron is. This, so channeltron electron multiplier. So I'm not sure what an electron multiplier does. Channeltron electron multipliers are durable and efficient detectors of positive and negative ions as well as electrons and photons. Okay, it's another device for detecting particles. Pretty straightforward. It's interesting all the different devices that they have made to detect all of these things. I'll go ahead and save these links as well. Maybe I shall save them in my make a lab folder for them. Right? These are my lab 2 links. And I also put the electromagnetic spectrum image in that folder. Right? However, above the threshold for excitation of the 63P2 states, I'm right here, 5.46 electron volts. No discrimination between the 63PO and 63P2 metastable states is possible with this method. Such a discrimination was feasible in an experiment with fluorescent emission. Was induced by laser light tuned to the 63PO to 73S1 or 63P2 to 73S1 transitions after the 6,3-PO and 6,3-P2 states have been excited by electron impact. So this gets deep. The intensity of the fluorescence is a measure for the excitation cross-section of the particular metastable state under study. The cross-section for excitation of the 6,3-P1 state cannot be attained with the two methods because of the relatively short lifetime, 120 nanoseconds, of this state. Okay. However, the intensity of the fluorescent light, 254 nanometers, from the 6,3-P1 to 6,1SO optical decay just mentioned is a measure of the excitation cross-section of direct electron impact excitation, which we noted earlier. Recently, these excitation cross-sections have been calculated for the first time using an R-matrix closed coupling method. As a summary of all experimental and theoretical results, the behavior of the cross-sections or excitation of the lowest 6,3-P012 mercury states is shown in figure 4 for energies from the excitation threshold up to 6 electron volts. So let's look at figure 4. All right, so this is the one on the left right here. Cross-sections for the electron impact excitation of mercury state 6,3-PO, energy loss of 4.67 electron volts. And normally it is, what was it, 4.9? And 6,3-P2, energy loss of 5.46 electron volts versus energy. These data are estimates taken from various measurements and calculations in the literature and are uncertain up to 30% because of the lack of precise absolute measurements. It's a pretty big uncertainty. Well, I guess in general, but suppose it's pretty close for what we're measuring, something so small. The relative as well as the absolute values of the cross sections are uncertain by 30% because of the lack of precise absolute measurement. So he agrees it's a pretty big error margin. Each of the three curves exhibit a sharp increase above the excitation thresholds, and two curves exhibit an additional sharp or broad maximum before decreasing at energies above 5.5 electron volts. The maxima occur at 4.7, 4.92, 5.2, and 5.59 electron volts. At these energies, there is a significant probability for the incident electron to be captured temporarily by the atom and to form a negative ion. Interesting. These negative ions live for about 10 to the negative 3 seconds, so that's about what? 10 picoseconds or less if the widths of the peaks are 20 microelectron volts or more. The mercury atom finally may be found in the ground state or in one of the excited states, provided that energy conservation prevents such a decay. The classification of these mercury resonance states, mercury ion resonance states. So you see that little dash must mean it's a negative, has one negative charge from the captured electron. Resonance states has been controversial since their first observation by Kayat et al. Fano and Cooper. Kayat et al. Fano and Cooper suggested that these resonances should have mercury ion configuration 6s6p2. Several classification schemes have been suggested that differ particularly in the assignment of quantum numbers to the structure of 4.92 electron volts just above the 6,3-P1 threshold. Furthermore, not all of the compound ion states that were expected by Fano and Cooper and Hetto have been fully confirmed. The example of a recent experiment that helped clarify the situation is the investigation of the circular polarization of the 254 nanometer fluorescence emission excited by polarized electrons. And let's check figure 5 first before we talk about it. So we have a schematic diagram of the apparatus used by Wolke et al. For measuring the circular polarization of 254 nanometer fluorescence light emitted at the electron's impact excitation of mercury atoms with polarized electrons. So it looks like we have a laser, a 90-degree deflector, a cathode, magnetic coils, electron lenses. Looks like an atom beam. So experimental physics, I guess they designed this thing. I mean, it's an interesting thing about physics. I mean, cutting edge physics. You can't just like go to the store and buy whatever it is. It doesn't work like that. You have to build it, design it, and build it. That's why I'm more interested in theory. I don't think I'm interested in building machines and devices, but somebody has to do it, or you wouldn't have any of the marvelous devices we have right now. So let's go back to that section. Figure 5 is a schematic diagram of the apparatus. A GAAS photocathode in ultra-high vacuum is irradiated by circularly polarized laser light, with the result that longitudinally polarized electrons are emitted. After deflection of the electrons to 90 degrees, the polarization is rotated by two magnetic poles to 90 degrees to the perpendicular to the XZ plane. The electrons then pass through a differential clumping station, where they are again deflected to 90 degrees. A lens system focuses the polarized electron beam onto the mercury beam target. At the target, electrons are polarized along the y direction. Some of the mercury atoms are excited by electron impact. A photon, but this reminds me of my stellar astronomy class where we uh, discussed how collisions excite atoms. So you probably could look at those notes a bit and get a different perspective on it. But I know we're talking about stars and how at first astronomers thought that different stars were composed of different elements because when we study the spectrum from stars, we see different elements in the different stars predominantly. But what it turned out is at different temperatures, the collisions in those stars uh, happen between at different speeds and different energies, and therefore the certain elements respond better at certain energy collisions. Just like how you know Mercury has a specific frequency of emission of its energy and very discrete energies at which it can be excited with impact. Basically, beyond a certain level, certain atoms just will not get impacted, will not get excited at all because the energy is too high to to hit that exact quantum level where they're excited. So basically, you can have a star, two stars that have the same compositions, but because of their size, the difference, the pressure and size of one, and the heat of one is so much greater that the velocities in one star can excite this particular energy in this certain type of molecule, and the energy excited in the other star excites a different atom or molecule. And thus, when we study the spectra, we might find that this element is very predominant in this star, and a different element is predominant in that star, even though the overall composition of each star is the same. So it took a lot of study and calculation and uh, observation to discern that these stars are all composed of pretty much the same things with traces of other things, and the different temperatures determine what we see in that star. So now we can look at the spectra of a star and look at what elements are predominant, and thus know the temperature of the star because we know at what temperatures those atoms or molecules can be excited by collision. So this reminds me of that. So I'm pretty sure I'll mention that as one of the applications. So of that knowledge. So stars. stellar astronomy. Different atoms and molecules excited at different temperatures. All right, so I'll make sure I look into that and have some detail on that for my paper. So where was I? A photon analyzer system measures the circular polarization of 63P1 to 61SO resonance line, 254 nanometers ultraviolet, by lambda over 4 plate or wavelength over 4 plate in a linear polarization analyzer as a function of collision energy between 4.5 and 7 electron volts. See, 4.9 is between that range. A photon analyzer detects photons that are emitted in the direction of the electron spin polarization. The result is shown in figure 6. The significance of the result lies in the fact that around 5.2 electron volts, the circular polarization is negative. A formal analysis shows that non-resonant exchange collisions result in a positive circular polarization. However, the temporary formation of, let's read that again. The result is shown in figure 6. The significance of the result lies in the fact that around 5.2 electron volts, around 5.2 electron volts, the circular polarization is negative. All right. A formal analysis shows that non-resonant exchange collisions result in a positive circular polarization. However, the temporary formation of and I like how they actually, uh, part of the sentence breaks off at the image. A lot of times I try to complete my sentence on the page, but notice that there too, I didn't even realize it. So maybe I'll implement that in this next paper, how they, it's fine to break off a sentence. However, the temporary formation of the mercury ion after it absorbed the electron, ion state with a total angular momentum of J equals 3 over 2 results in a negative value, whereas a negative ion state with J equals 5 over 2 leads to a positive value. I feel motivated to study some quantum mechanics. This helped to establish the existence of a broad J equals 3 over 2 resonance that is invisible in the 6,3P1 excitation cross-section, but was later shown clearly in the 6,3PO excitation cross-section. So all of this talk of the different levels just still is going over my head. The most probable classification scheme of the H3 ion 6S6P2 resonances is table 1, 1824, 4P1 have 4.55 electron volts seen only in the elastic cross-section. P32, 4.7 electron volts seen in the 6,3PO cross-section. P52, 4.92 electron volts seen in the 6,3P1 cross-section. But in the 6,3PO cross-section as decay in this state is strongly suppressed because of the centrifugal forces of the high orbital angular momentum that the emerging electron must carry away. In D32, 5.2 electron volts seen in its broad maximum in the 6,3PO curve, invisible in the 6,3P1 curve, and 2D52, 5 electron volts seen in both 6,3P1 and 6,3P2 curves. Man, that's some detailed analysis. How does the behavior of the cross section shown in figure 4 influence the output of the Frank-Hertz experiment? I'm not even sure. And they mentioned figure, what did they mention? Figure 6. So we didn't look at figure 6 yet. Circular polarization right here. I positive current minus negative current over positive current plus positive current versus energy for 254 nanometer fluorescent light emitted at the electron impact excitation of mercury with polarized electrons here. The positive current and negative current are the intensities of light transmitted by the filter for photons with positive and negative helicity, or left or right circular polarization, respectively. So now we're in section 5. We're on the next to last page, so this would really be the last section. The next is the references. The shape of the Frank-Hertz curve depends on the tube design. Now this seems important and something I can catch. Shape of curve. One of the two questions raised in section 2 has already been answered in sections 3 and 4. The energy loss obtained by recording the Frank-Hertz curve is not the result of simple inelastic collisions where the electrons lose all their kinetic energy. It is a complicated process where exchange collisions and the formation of short-lived mercury ion states dominate. Interesting. So it's not just simple inelastic collisions. There are inelastic collisions. Also, short-lived mercury ions. This is page 4. Well, section 5 is good. It's interesting. The second question is, why is the observed energy loss approximately 4.9 electron volts instead of 0.67 electron volts, the energy of the first excited state? So the observed energy loss is greater than the energy of the first excited state. That seems to relate to that previous graph. So this is the first excitation state, 4.67. It seems to be here on the graph, this little bottom peak. The answer can be found by examination of figure 4. As an electron passes from the cathode to the control grid, it gains kinetic energy. So we're looking at figure 4 right now. At a given point in the transit, the kinetic energy is proportional to the product. At a given point in the transit, the kinetic energy is proportional to the product of the potential difference times. At a given point in the transit, the kinetic energy is proportional to the product of the potential difference times the fraction, the electrode separation that is traveled minus the kinetic energy losses due to prior collisions. Let me try to write this out. As the electron passes from the cathode to the control grid, so I have a cathode on the left, I have an anode on the right. So the electron is passing from the cathode to the control grid, gaining kinetic energy. Kinetic energy is going up. At a given point in the transit, the kinetic energy is proportional to the product of the potential difference, so I'll put change in V, times the fraction of the electrode separation that is traveled. I'll say D traveled, times the fraction of the electrode separation that is traveled, minus the kinetic energy losses. Oh, D traveled minus D total, minus the kinetic energy losses due to prior collisions. Right? So the kinetic energy is proportional to, at any given point, the kinetic energy is proportional to the change in voltage times the distance, the fraction of the distance traveled divided by the distance total, minus the kinetic energy prior loss due to collisions. So on the right side. Right column. Okay. Whenever the kinetic energy reaches 4.67 electron volts, excitation of the 6-3 PO state is possible, but only a few electrons give up 4.67 electron volts of kinetic energy by exciting the 6-3 PO state due to its small cross-section, with the result that the electrons have a large mean free path. Those remaining continue to gain kinetic energy and reach 4.9 electron volts or more, while many of these electrons excite the 6-3p1 state, as it has a high cross-section above 4.9 electron volts. Some electrons do not yet even lose their kinetic energy and continue toward the control grid and gain as much as 5.5 electron volts or more, enough to excite the 6-3p2 state. The tendency for a larger fraction of the electrons to gain enough kinetic energy to excite the 6-3p1 and 6-3p2 states increases with decreasing mercury vapor pressure and depends on the tube design as explained in the next paragraph. So I'm understanding this. So basically the electrons go through, but you can say so you could almost imagine like the mercury atom is almost like a catcher's mitt, and at a certain energy of excitation, it only has a certain size of mitt. So even though the first excitation level is 4.7 electron volts, the area within which it can catch the electron is relatively small. But at 4.9, which is the 6-3p1 state, the area at which it can capture an electron is wider. Therefore, there's a greater probability of capturing the electron at that energy level, and thus we see a lot of that. So that's pretty simple. So 4.67 evolves small. So the 4.67 is the 663PO state. However, the 4.9 electron volt larger section and that is the 63P1. I might not even mention this, the P1 and 63 and all that stuff in my paper, just the energy levels. I could understand the energy levels, but the going to take me some refresher, not only refresher, but some detailed study of the electron state. So this check back, I'll be reading my quantum physics book more in preparation for the fall. All right, so now we'll get into the tube design. The peak spacing in the Frank-Hertz curve depends on the conditions under which the experiment is performed. Hold up. The peak spacing in the Frank-Hertz curve depends on the conditions under which the experiment is performed. Oh, I see. Is that, not the. That, the peak spacing in the Frank-Hertz curve depends on the conditions under which the experiment is performed. It is demonstrated by a model calculation simulating the outcome of a Frank-Hertz experiment. Results are shown in Figure 7. All right, simulated Frank-Hertz curve for the cross section of pH D equals 4 megabar centimeters, where pH D and D are mercury pressure and distance cathode anode in the tube respectively. Okay, the same for pH D times 4 equals 20, with which the Frank-Hertz experiment usually runs, given the most attained peak spacing of 4.9 volts. Okay, so I don't understand this graph. I'm gonna have to ask Professor about this one. That's Figure 7. And I believe I labeled my question properly. Right? These calculations should not be taken too seriously because of very crude approximations made. Homogeneous electric field, isotropic differential excitation cross-sections, simple Maxwellian electron energy distribution, neglect of repeatedly elastic collisions that lead to small energy losses as attained in swarm experiments and other simplifications. The important inputs of these calculations are the mercury vapor pressure, the distance d between cathode and anode, and the cross-section shown in Figure 4. So the Figure 4 is starting to make more sense. It's about the cross-sections for electron impact. So that's why, so I see. So the bottom one here, right here, there's an excitation, but the cross-section on this axis is very small, so there's not that many that can hit it. But this cross-section is pretty big, so it can hit it. And this cross-section is pretty big. Okay, so that makes sense. Right? These inputs determine the relationship between the mean free path and the energy gain within the mean free path. Curve 7b represents the situation most nearly realized, leading to a peak spacing in the Frank-Hertz curve of about 4.9 volts. Makes sense. If the product pH cross D is 5 times larger, the spacing is calculated to be only 4.8 volts, 7C. All right. Starting to make sense. Indicating that in this case, the 6-3-PO state has been excited. Energy loss of 4.67 electron volts, with a significant probability in addition to the 6-3-P1 state. Notice I mentioned probability earlier. If, on the other hand, the product pH cross D is 5 times smaller than normal, a considerable number of electrons may even gain 5.5 electron volts to excite the 6-3p2 states, which result in a peak spacing of 5.15 volts or more. It's still unclear how even though different electron volts are hit, it still emits the same wavelength. All right, so indebted to Professor R. St. John for reading the manuscript and making valuable suggestions. So that's a short paper, but look at all of these references. So nice paper. I understand the experiment a bit better, and I'll go back again to my picture from my experiment. So let me copy this over if I can. I want to copy just the cam. There we go. All right, so if you look at this, the again the bands, you can see the bottom third row where so now notice that the band moved downward. So that must mean that the cathode is above at the top and the anode is at the bottom, so the electrons are moving downward. And so the first band is excited. Then as the voltage increases, the electrons that lost their energy by exciting the first band at the top excite again and excite the second band. And the same thing happens to the third band. And we understand that the cross section for the 4.67 electron volt capture is so small that it moves a little bit forward and hits the 4.9. And it looks like we have several series of 4.9 because after it loses energy on the first band, it starts up again until it hits 4.9. And that's why, now I understand why the emission is always the same. Because on the first band, it loses energy. Then it starts again. And when it hits 4.9 again, it causes a change in the energy level of the atom, which then drops level and emits. Then it starts up again and it repeats on the third one. So it's literally 3 different instances of exciting the same amount of energy. So I'll make a note of that. That is interesting. Only if somehow the electron could continue accelerating faster, even though it lost a whole lot of energy on the last line, could it possibly excite an even higher level? You know, it dumps all of its energy or nearly all of it. It's excited again, dumps nearly all of its energy at the same 4.9, excited again, dumps nearly all of its energy at the 4.9. So doing those dips. So each line of color is basically a dip. So awesome. Thank you for joining. Here are my links again. Be sure to subscribe, like, share, all that good stuff. Meet me on my Discord. We can talk about science, math, whether physics, astronomy, calculus, linear algebra, whatever. Have some places for study groups there as well. So come along, talk, let's chat. And I will do some math homework. So usually I don't do problems on homework until after it's past due. So I'll just do that off camera, but I'll review it in the future. And but I will be back, if not later today. I will be back later today to read some quantum physics. I've been getting behind on that, so I'll really hustle on my math homework, and I'll be back tonight to do some quantum physics reading. So have a good one, you all.